our first talk in the session, and the first speaker is Hans Zwart with the talk titled "The Range of C0 Semigroups." Very promising title.
Thank you. I will share my screen. Yeah, now we start with this one. Okay, welcome everybody. I just want to, this was somehow a research or results which I almost forgot, and because of the conference, I remembered that I had something lying, which was just on my notice board already for many years, and I tried to rewrite it, but the ink was almost gone, so I had somehow to rethink everything again. But okay, I managed. That's not the problem. But it's a funny story that it just started like this. I want to start a little bit different so that you see where my idea came from. So we just have a semigroup on a Hilbert space, and just the strange thing that I just don't denote my Hilbert space with an H, but with a Z, yeah, just okay. And then there is this nice and at the same time very surprising result that if this semigroup is, say, bounded away from zero at some positive time, then it's bounded away for all time. Yeah, so then if you have it, say, bounded away, if you have this property, this one, for one t, then you have it for all. Yeah, that is the importance that I want to say. Then you have it in, and this is already okay. This is known, but it's still surprising. That means basically that the operator, yeah, is left invertible for every time. And the nice thing is, that's quite surprising. I found that very surprising. So there really exists a C0 semigroup, which is really the left inverse of my original semigroup. So if this property is the first one is satisfied, then that means that basically the semigroup is left invertible, and the left inverse can be chosen as a semigroup. One remark I want to make: this semigroup, this S of t, is not unique. Yeah, it need not to be there. I built examples where I constructed more, but okay. And now you ask the same question on Banach spaces. So on Banach spaces, because the first item was basically just a semigroup property that you have one and use the semigroup property, you get it for all. That is just so you have again, and that if you have it for one, if you have one time, then you have it for all time. And of course, that's the same as saying that the operator is left invertible for all t. But the last item is really unknown. So I pose this as an open problem to the community. Is the same theorem which holds in Banach space or in Hilbert spaces also true in Banach spaces? And I don't know the answer. I believed for a very long time that the answer was no. And so that that I could construct a counterexample, but I was never able to construct a counterexample. So the thing is really open. So this is what I had, and as the warming up, you could say, and as an open problem to the community. So this gave me the idea, and let's go to the next page. So this gave me really the idea. Let's move this. Okay, this really gave me an idea to look at properties of the semigroup which holds for one t, and if it then holds for all t. Now the property that is, say, this t0 is left invertible is the same as saying that the range of its adjoint is the whole space. So I'm back to the Hilbert space case again. So I'm here at the Hilbert space case, but okay, that's not so important. That the range is the whole space. So you could say if the range is for one time instant, the semigroup is the complete space, then it holds. Now I forget about, because I'm in the Hilbert space, then there is basically not that much difference by looking at the semigroup or its adjoint. So I forget the adjoints and I ask myself. So I reformulate these results first. And so I have a semigroup which is surjective for some positive time, then it's surjective for all time. And that gave me the idea, and can I now think about this thing and see if there are other properties? So basically, is there another property such that if I have it for some, I have it for all? And I was thinking, okay, this is the whole range. So for the whole, if the semigroup is surjective, then it's true. So I asked myself the question, if the semigroup has closed range for one time instant, does that imply that the semigroup has closed range for all time instances? So that is what I asked myself. And okay, so I gave that some thoughts. These were just a puzzle that I gave myself, and okay, I was luckily able to solve it and never wrote it down. Now for the conference, I have written it down. And the answer is no. And I will show it by means of an example. And it's nice that I can, because I can make a picture, and the picture I still had on my paper, I could decode it, and that's why I could construct the counterexample again, because the rest was almost faded away. So the example really shows more. That's basically, so you can go from closed to non-closed and back to closed again, and you can make alternating. So you can really jump and from closed range to non-closed range and back again. Yeah. So it's not that you are you only have one option. No, you can just jump all the way and from closed to non-closed. I just okay, I can go slowly through the example because I have time enough, but okay, just so I introduce the Sobolev space on the interval 0, 3, which is 0 at the right-hand side. So they are, okay, Sobolev space are all L2 functions for which the derivative exists in L2. And it's a Hilbert space, and with, say, the standard norm, you take the L2 norm of the function, and you take the L2 norm of the derivative. And this is a Hilbert space. So the only thing, somehow it's the 0 here. So it's the 0 here. That means, and that it's at the right-hand side, it is 0. It's just my notation. And now I built my semigroup, and this is the most complicated slide I have, and I probably will make a drawing and tell you what I have. So I have two components, the x1 and the x2. And the x1 is, say, smooth, and that is just, this comes out of this h1 0 space, and is just the L2. Yeah, and now I can probably give me an extra space. Yeah. Now I first make a drawing. What do I do? So I have here my space 0, 3. And this is in where x1 comes from. And this is, say, on h1, 0. Then I have here my space, my interval -1, 1. And here is in where x2 comes from. Yeah. So, and this is just in L2. And what is now the whole idea of the proof? Basically, just make it in. I do the left shift. So on this interval, I just have the left shift. On this interval, x2 is just the left shift. So we all know that that's our standard example of a nice C0 semigroup. So it's just the left shift. And that's why I need to have it 0 here, because of course 0 comes in. But then there is the trick. At this point, at the point 0, I let what, and now let's make it into green. Here is, say, basically x1 shifting out. You can see here is somehow x1 shifting out. But what happens, everything that shifts out here enters there. Yeah, and is added. So here I should make a plus. So there are basically two shifts. Just the x1 is shifted to the left, the x2 is shifted to the left, but in the second interval, I at the point 0, I add what comes out of this interval. So here is basically, let's make it a drawing a little bit. So suppose as an initial condition, I would have something like, say, this one as x1, then after a while, I will have it. So if time, I will have it here. It shifts out to the left, and the first interval shifts in to the left there, and of course, and where I don't, and then
Hans?
it. Okay, that's
Hans?
Yeah.
Hans, sorry for
Yeah.
interrupting. Sometimes you have slow internet and your voice is breaking. Could you
I will
please
see what I can do on it.
you can switch off your video, your camera. Then
No, I'm here on wireless. I will do the cable. I think the cable is better.
probably yes. Or otherwise you can switch off the camera and the voice will occupy all the internet channel.
Let's see.
Didn't help.
One moment. I just try to. Okay. Oh, everybody is now frozen.
Mhm.
Is it now better?
Yes, it is now better, but it is not always.
No, okay. I can switch off I can stop video. Yeah?
Yes, just switch off the camera and
I've switched off the camera now.
thank you.
Okay, thank you for your comment. Yeah, that's so let's see, because I will explain it a little bit more, but okay, it's just because I have time and I can just go that. And so, and now I have to go blue again. So what happens? I have on the first line and on the second line, I have just the shift, but on the second line at the point 0, what is shifted out of the first interval, so of the top interval, I should say better, comes in, is added and to the shift of the at the second interval. And now I have to, yeah, let's see, yeah. So now I go back, and that you see, huh? So you see here, so I've tried now to do it. So you see that the y1 is nothing else than the shifted of the x2, x1. So I have at the top level, I just have my shift. And at the y2, the second component, you see it here, is the shift of the second component. And here, on the interval minus 1, 0, I add by basically what came out of the first one. Yeah, this bold one is just the indicator function of the interval, and I did not want to write all indicator functions down, so you just have to x1 of t plus psi. If t plus psi does not lie in 0, 3, then it's 0. So this is the idea. And now together with this picture, so I hope you can keep this picture into mind. I will tell it, because what happens now? I look now at this semigroup. You can prove that it is a semigroup. I will look at this semigroup at different time instances and see whether the range is closed or not. So that I will do next. So that's here, yeah. So we look. So here we have time 1. Now time 1, so let's go back just to have the picture. At time 1, you see that this x2, because the speed is 1, has been completely moved to the interval minus 1, 0. So it's the second component is 0 on the interval 0, 1. And the x1 component, yeah, it's 0 on the interval 2, 3, and next left to it on the interval 0, 2, it's arbitrary. It's just a shifted version of x1. But what did I came in? So I added this shifted x2 and I added it to an x1. So again, I have to go 2 times forward. So the second component equals 0 on the positive spatial interval, and on this it consists out of an h1 plus an h2 function. And now you see this L2 function is arbitrary. That is just a part of x2, which I had. And so I can always cancel this h1 component, and so I can get just an arbitrary function of L2 and on the interval minus 1, 0. And so I get that the range is closed. The range is just L2 on 0 on minus 1, 0, and 0 on 0, 1, and the top one is there. Now I repeat this. For time t is 3. And let's go to the picture, because I think if you have the picture in mind and you know what's going on, if I now am at time 3, you see that the x1 component has completely shifted out. In the top function, so at this part, I have only the 0 function. And what happens? So the x2 part has also disappeared completely, because I shift with speed 1 and I'm already at time 3. And you see, though, the x2 has completely shifted out. And what do I get? I just have here on the interval, on the interval minus 1, 0, I still have a piece of my x1. But this x1 was an h1 function. You see it here. And so that is the whole trick. Yeah. That time the x2 is 0. And so the second component just consists out of the shift. The first component is completely 0. And since h1 is not closed in L2, the range of t3 is not closed. Then I go a later time, and you see if I just wait long enough, because I have shifts on a finite interval, if I just wait long enough, then the semigroup will be equal to 0. or the semigroup at that time instant will be equal to 0. So then the range is closed again. So you see, I went from t is 1, there it's closed. At t is 3, it's not closed. And t is 4 greater than 4, I am closed again. Now, if you get this this idea of this semigroup, then you can see that I could build even more of it. I could make more of these intervals and let them just change, and so I can jump between closed and non-closed as many times as I want to do. So that shows that this closeness of a range is not say a semigroup or a time-independent property. Then I come already to the end. So let's see. The first part, so on the left, invertibility of semigroups, I followed a paper of mine already 10 years old, but the result somehow comes already from a paper which is somehow 40 years old, Louis and Wexler, where they used also system theory ideas to get it. And that is it. And it was Xu and Zhang also in 2009 contributed to it. Yeah, and I want to thank you for your attention. I think I was a little bit fast, but okay, if there are any questions, then I'm always very eager to answer them. Thank you very much.
Thank you for your attention, for your very nice talk. It was really interesting. Questions, please. We have 7 minutes for discussion, for questions. Please.
So I have a question.
Yeah.
Please.
So my question is basically that you have this counterexample on a Hilbert space. Can you do something like this example? Have you tried doing this on a non-Hilbert space to get a counterexample to your original problem, which is that you don't get a left invertible, you don't get a semigroup such that STTT is identity operator?
Yeah, I tried things like this, but okay, good that you asked, because this was somehow, these kind of constructions gave me also an idea why they were not unique in somehow. And I tried to construct a counterexample like this in Banach spaces and show that it was not left invertible with a semigroup, but then I turned out to be wrong. Yeah, and that somehow. So I played with these ideas. Yeah, maybe not long enough, but I spent some time in it and to construct a counterexample. But the counterexamples, you're right, they were really based on shifts and doing shifts on funny spaces and let them go to other funny spaces, like I had somehow. Now, yeah, in this picture, we're just going back. I don't know, this funny picture where they go from the one to the other. Yeah. And unfortunately, it didn't work.
Okay. I have another question, if I may.
Yeah, please.
Yeah. So my question is, so the intermediary results were true that TT is left invertible for all time T. So in a Banach space, those intermediary results were true. So what goes wrong in the proof that it doesn't work for Banach spaces?
Okay.
For the semigroup part?
Yeah, I will. I go there. Now let's go to this one. Yeah.
Yes.
The proof is based on ideas from system theory, surprisingly. So basically, what you show out of this condition, you show that then an equation like this is solvable, A star x plus, I hope I say it correctly, is minus identity. You assume that the semigroup is exponentially stable. That is not important, yeah?
Yeah, correct.
And then you can somehow, from this, you rewrite it into, now I have to think, you bring the identity to the other side, and X is invertible. That's important. X is invertible, so X, okay, cool. X is invertible, I know, oh, I have to go. And then oh, but this is a really, you see it here, solvability of this kind of equations is really, the idea comes from system theory, let's put it like that, why to look at a system like this, and that has to do with observability, which are notions from system theory. But then you see this equation, if you are in a Banach space, yeah, wait one moment, where is then this identity? If A star maps into dual space, yeah? So you cannot, these are called Lyapunov equations, and I don't know how they go in Banach spaces. And the idea is then, let's see, you do a little bit, I think you do this plus X inverse. I think you do it like this. Is X or is minus, oh no, now I make a complete mess of it, sorry. Plus X is 0, this is somehow the same thing. And since X is invertible, basically this tells me that okay, you know that A star plus X inverse generates a Z0 semigroup because it's just a bounded perturbation of A star. This identity gives you, and that it's in the weighted inner product with X as the weight, it is the left inverse. So you have to put you make, okay, I can do it, I know it now. You write it like this. And then you say, hey, this operator A star plus AX inverse generates a Z0 semigroup because I'm in a Hilbert space.
Yeah.
Right, and then you basically you integrate this equation, and then you see that the semigroup generated, this semigroup generated by this operator is the inverse of that of A.
Yes, and this is where
really
Hilbert
a Hilbert
space.
space technique.
Yeah, correct. Now I get it. Thank you.
Yeah.
More questions? We have time for questions. Please. Okay, then I have a question. What do you think? What corollaries may it have? What that kind of questions may lead to?
The range question or the inverse of the semigroup?
Both. Of course, it is of theoretical interest because it's a fundamental questions. Interesting to discover such fundamental questions, but maybe there is also some practical motivation. Maybe this open problems is connected with another open problems. I just don't know. This is why.
I don't know it either. I'm not. I found it very surprising, let's put it like that. I thought that since this surjectivity is somehow maintained, or this property which is there and left invertible is maintained, I also thought that when a semigroup had a closed range, it would always have a closed range. But so it's it was for me more as a puzzle, and I don't know precisely the consequences of it. Yeah. I have thought about it, but I have not seen a relation with an other problem. The left invertible, I found it very surprising as well that you could take the left inverse as being a semigroup. I never expected that, yeah, because it was a, and I don't know how you could, gave me a little bit more insight into semigroup theory and how you can build things. But I don't see it, how it related into another problem, yeah?
Probably this will be clear later.
Yeah, I hope so.
Probably. Also, I have one more question for you. Have you submitted those as an open problem in semigroup theory?
Yeah, it is set. So this, so let's go to the next page where it is. Yeah.
I mean,
There's
we are
an
collecting open problems. So if you send this problem to our list, we one perfect day will publish it. But
okay, no, I can, because it is posted in the paper on left invertibility, where I basically do the proof for the Hilbert space case. There at the end, I say, okay, I don't know if it's true for Banach spaces, but I can send it in once more, yeah?
yes, well, if you already submitted it to the list, because
No,
the list was highly circulated in the previous conference,
yeah,
and it is not actually um, much more changed. So we do not circulate it again. Probably this is wrong, but well, nevertheless,
no, I could
please send it.
I could add it. Yeah, I have to formulate it a little bit, but then I can send it.
Okay, thank you. Thank you again for the very nice talk.